Hi everyone, my name is Yipeng Zhang. Today I will talk about our recent work, minimizing the regret of an influence provider. So we studied this problem under the OH advertising market, which is short for out-of-home advertising. And why this problem interested us? The first reason is it's valuable. It is more than $6 million in 2020 and will be more than 50 million. The second is because most, if not all, existing work aims to find a billboard for one single advertiser to maximize the influence. Different from them, in our work, we are trying to maximize the profit for the single host who is dealing with multiple advertisers at the same time. The third reason is the hardness of this problem. We prove it is NP hard to approximate with any constant factor, which means this problem is non-trivial. And also I will talk about the solution and the experiment. Now let's start with the existing work. Here we have a host and the advertiser. The host has a lot of billboards. Each of billboards has an influence and a cost. And the advertiser tries to buy some influence from the host. And the influence is coming from the billboard showing advertising. So for the existing work, they are trying to find a billboard seat for one single advertiser under her budget, such that this billboard seat can maximize the influence for this advertiser. But actually, in real world, we find the OH advertising has a new business model. So the host need to dealing with multiple advertisers, and for each advertiser, they are not just has a budget, but also has a demanded influence. Therefore, based on the existing market, we design our problem as following. We still have a host and advertiser, and the advertiser will try to make a contract with the host. In this contract, there is a request, which is the number of people this advertiser want to influence. And also there is a payment. So after the host receives the contract, she will try to find a billboard seat for this advertiser. The billboard's influence has to be larger or equal to the demanded influence from the advertiser. After the request is satisfied, the advertiser will pay the money to the host. So, formally, we will input a billboard seat, advertiser seat, where each advertiser has a budget and a demanded influence. And we're trying to find a billboard seat for each single advertiser. And we try to maximize the profit of the host from all advertisers. But the first problem here is how do we define the profit? In a simple way, we can define the profit as the total payment from all advertisers. But is that good enough for our problem? I will tell you the answer from the following examples. Let's say we have a host and advertisers, and they have a contract with $300 to influence 300 people. But the problem is that the host can only influence 200 audience for this advertiser. But because in the contract, the host needs to influence 300 audience, which means the request is unsatisfied. Therefore, the advertisers will not pay $300 to the host. So let's assume the advertiser only pay $100 to the host. So this is called unsatisfied penalty. In the second scenarios, the host can influence 400 audience, but in the contract, she only needs to influence 300 audience. Therefore, the extra 100 audience is like a free service. So this is what we call excessive influence. This is also a loss for the host. Therefore, instead of maximizing the profit, we are trying to minimizing the regret. And the regret covers the satisfied penalty and the excessive influence. So we also prove that the minimizing regret can cover maximizing the profit. If you are interested, you can have a look at our paper. So this is the objective function. And we name our problem as minimizing regret for the OOH advertising market, the MORA. Here the L is the budget of the one advertiser. The I is the demanded influence of this advertiser. The SI is the billboard assigned to this advertiser, and the ISI is the influence of this assigned billboards. So this is how we define the regret for each advertisers. The gamma here is a penalty ratio because of the unsatisfied demand. The gamma can be from 0 to 1, and if the gamma equal 1, it means the host can receive the fraction of the payment as the same fraction of influence that has been satisfied. And if the gamma equals to 1, if equals to 0, it cannot receive any penalty. We already shown in our paper that MORA is non-sum monitor and non-monotone. Therefore, the greedy-based algorithm may not have a good result. And also, we have proved the MORA problem is NP hard to approximate with any constant factor, which I will show you later. So, to solve these problems, we first introduce a baseline, which is synchronous greedy. And based on this synchronous greedy, we introduce two different random local search framework. The first one is based on the advertiser-driven local search. The second one is billboard-driven local search. And I also will talk about it later. So here I will show you how we prove the hardness of our problems by reductions from the numeric three-dimension matching problem. So in the N3DN problems, we have three integer sets, and each of them has n integers. So in the N3DN problem, we are trying to find a matching relationship that in this relationship, we will get only one single integers from each x, y, and z, and the sum of those three integers has to be equal to b. And because the size of x, y, z are n, so we have those n triples, and the sum of each triples has to be equal to b. So in our problem, we assume we have n advertisers. For each advertisers, the request is equal to b, where the b is the bound in the N3DN problem. And we first divided the billboard set to three pieces with the same size. Then we mapped the billboard in the MORA problems to the N3DN problems, just like the billboard's influence is equal to the integers in N3DN problem. Therefore, for the n advertisers, we can find n billboard datasets for each of them, and the influence of each billboard set has been equal to bi. So for the N3DN problems, we will find the n triples that the sum of each triples is equal to b. And in MORA problems, the influence of each billboard set is equal to I. So if we can find the solutions in the Amsterdam problems, we also can find solution for moron in a polynomial time and vice versa. Now I will introduce the synchronous greedy. Let's say we have a billboard set and we also have 3 advertisers. So we first find the billboard to each advertisers which can maximize the equation shown here. And we will continually find the billboard sets for each advertisers until we out of billboards, or we can make every advertiser satisfied. Next, I will show you the randomized local search framework. The first type is advertiser-driven local search. For the advertiser-driven local search, we will first randomly assign a billboard to an advertiser. Then we will run the synchronous greedies to assign the remaining billboard to all advertisers until we are out of the billboards or everybody is satisfied. But after that, we will do the advertiser-driven local search. We will try to exchange the billboard sets between advertisers if we can find a smaller regret. But sometimes the advertiser-driven local search may not find good solutions. So here is the examples. Let's say we have advertiser A1 and A2. And we're trying to find a better solution, so we try to exchange the S1 and S2. But after that, you can find actually the total greedy becomes larger. So how can we achieve a better solution? Instead of exchanging the whole billboard set, here we try to exchange just one billboard from S1 and S2. Therefore, we can just achieve the demanded influence, and the total regret will become to 0. This is the second local search framework strategies I want to introduce. We call billboard-driven local search, BLS. In the BLS, the first step is same as the ALS, but in the second part, the billboard-driven local search, we will use the 3 different strategies. The first one is we try to exchange 2 billboards within 2 datasets. For example, here we try to exchange O4 and O5. And the second one is we try to remove 1 billboard from 1 advertiser if we can reduce the total regret. In the last one, we try to assign 1 unused billboard to 1 advertiser and remove the billboard if we can reduce the total regret. So this is BLS. In the experiment, we'll not only evaluate the efficiency and the effectiveness for all algorithms, we'll also try to figure out how the host chooses the customer, the advertiser, to reduce the regret as much as possible. So therefore, we introduce 2 parameters, the demand supply ratio, alpha, and the average individual demand ratio. The alpha is the total demand divided by the individual demand. So, which means when the alpha is larger than 100%, the demand is excessive supply. And when the alpha is less than 100, which means the host may has abilities to satisfy all advertisers. And the average individual demand ratios indicate whether there is a lot of smaller advertisers or the host will deal with some very big advertisers who has a very high demand and high budget. So based on the different demand and supply ratio and the average individual demand ratios, we cut our experiment to 4 parts. The low individual demand, the high individual demand, and the low global demand and the high global demand. And this is a data set. So we try to cover the different scenarios. So we use the 2 different data sets. One is from the NYC, the New York City. It records the taxi trajectories. And for the Singapore, we record the public transport record. Therefore, in the NYC, we have the roadside billboard, and in Singapore, all the billboards is located at the bus station. And from figure 1, we can find the influence, the distribution of billboard influence is totally different in Singapore and NYC. In the New York City, we have some billboards which has a very high influence, but in Singapore, the influence distribution of all billboards are more even. It is because when they build or design the public transport system, they will try to make the traffic volumes more even. That is why the billboard influence distribution is more even. The figure 2 shows the experimental result when the individual demand is low, which means the host has a lot of small advertisers. Each advertiser has a very low demanded influence and a low budget. So we first look at the figure A and the figure B. We can find the regret of all solutions becomes smaller when the alpha is increasing from 40% to 80%. It is because when the alpha and the individual demand are both pretty low, it means the advertiser's demand influence is very small. Sometimes the demand influence is even smaller than 1 or 2 billboards influence. In these situations, even the solutions assign 1 billboard to 1 advertiser, it will cause some excessive influence. Therefore, with a larger alpha, when the individual demand is pretty small, it is better scenarios for all solutions find a better result. The interesting thing is we find that in these situations, the BLS will try to sacrifice some advertisers. The BLS think we can has a very small unsatisfied penalties to reduce the excessive influence. And this is what we learn from the figure 2. In figure 3, we have a high individual demand, which means all of those advertisers has a high demand influence and a high budget. We first look at the figure A and the figure B. So, as you can see, in figure B compared with figure A, all solutions can achieve a very good result. It is because when the individual demand is large and when the alpha is less than 100%, all solutions can easily achieve a good result. And if the alpha is larger than 100%, it means the demand is larger than the supply, and no solution can control the excessive influence ideally. So, the third part is we comparing case 1 to case 4, and it's clearly when case 3 and case 4 with a very high global demand, all solution has a very high unsatisfied penalty. And from case 1, we know if the global demand and the individual demand both are very small, it is also hard to control the excessive influence. Therefore, we believe that in case 2, this is the best situation for the host to achieve a very small regret. The experiment of varying alpha, which is unsatisfied penalty ratio, shows that the alpha doesn't affect the excessive influence part, which is the orange part. It only affects the unsatisfied penalty part, which is the green part. With the larger gamma, the green part becomes smaller for all solutions. The experiment between NYC and Singapore shows that in Singapore it's more easy to control the recruit because we have more billboard and the distribution influence of all billboards are more even, so that's a better conditions for the host. And this is all for today's video. Thank you for your watching, and you're welcome to reading our papers or come to our Q&A part. Thank you.